Someone of you maybe in this room will remember that Alessandro did the keynote two years ago. And now he's back, I would say, with a new take on an old question. So, Alessandro SANTUZ, tell us, what about a dynamic system perspective on the gait selection in hypogravity?
Yeah, what about? Start the time.
Done.
What about it? So I don't know if you knew about that, but astronauts on the moon don't really like to walk or run. They do something slightly different. They like to skip. And this is Gene Cerner during his Apollo 17 mission, and several years after this he commented that he was doing this because of an added sense of security. Yes. And this prompted us to ask ourselves the question of why do astronauts prefer it, but from a neuromuscular perspective, because that's what we do. And we used the light well in this very department with an elastic support system to simulate Moon and Mars gravities. Of course, Earth doesn't need simulation. And we had 12 participants walk, skip, and run at speeds closely matching average preferred speed. And important thing is here, skipping is that sort of unilateral asymmetric gait that you've seen in Gene Cerner's video. We recorded electromyographic activity from 6 bilateral muscles, so a total of 12 muscles from the lower limb, and extracted muscle synergies with our own art package. And a typical output looks like that. You have, as we've heard before, 2 sets of coefficients, a set of timing variant muscle weights, which just tell us about the relative contribution of each muscles within a synergy, and then a set of time-dependent activation patterns which describe the time course of motor activities. And usually we normalize them so that the activation pattern goes from one touchdown to the next. Let's focus on these activation patterns and let's plot them in a 3D space. Of course, here I'm obfuscating the fourth synergy because a 4D plot would not be possible. But when we do that for 3 synergies, we see that they resemble kinematics, right? This is a very circular and kind of regular repetitive pattern. But we can tell a little bit more about these, and we can analyze how this trajectory is behaving in their own synergy state space. And if we zoom in, we will always find a pair of near neighboring trajectories that we can follow over time and see what their separation likes to do over time. And if we plot the divergence of these separations, we can see that those trajectories that do not like to diverge mass will be more stable than those that do like to diverge a lot. And this is the framework of the short-term maximum Lyapunov exponents. And I want to tell you one key principle that comes from our previous work. We had, a few years ago, the possibility to work in cluster with this very nice uneven surface treadmill. And when we look into the stability of activation patterns on this treadmill, independently of whether we are talking about walking or running, well, the stability of activation patterns increases, or in this case, the instability decreases when we add perturbations. So this, as a take-home message, means that challenges, so perturbations, stabilize the control, which is exactly the opposite of what we observe in kinematics, right? And we gave an explanation to this, considering that challenges are imposing constraints to the system. So now back to hypogravity. What happens when we do this kind of analysis in our setup? First of all, on Earth, well, at 1G, walking seems to be the gait mode that has the highest unstable activation patterns, making it perhaps the less challenging locomotion. And while on Mars simulated gravity, the message is not very different, the striking thing happens when we go on the Moon, well, when we simulate the Moon. we see that skipping comes up in the instability of activation patterns, and it is clearly statistically, because when you see that the letters are not shared, it means that the statistics are also not shared. Skipping seems to be the less challenging of all three. And here, another take-home message, we can say that skipping reduces the challenge of locomoting hypergravity. And we ask ourselves the question whether it might be a source of somatosensory feedback that is driving this adaptation. And to do that, we had to turn to an animal model, to a mouse model that Nicola introduced beautifully in the first talk of the afternoon. And mice, on the left side, on Earth, they walk brilliantly. They are awesome walker and runners. But on Moon, you see the left hind paw remains kind of lifted. They do an asymmetric gait. They have their own mouse skipping pattern. And we can quantify this very simply, just measure how long the paw stays in the swing phase, right, as opposed to the stand phase. And blue is Earth, gray is always Moon. We see that on the Moon, especially the left side, and this is something we still have to understand, especially the left side remains more lifted than the right side. So here comes the causal test we want to do to answer our question: what if, using mouse genetics, we remove proprioception? Well, if we remove proprioception, on Earth, locomotion is largely compromised, but on Moon, locomotion is not possible anymore. It's a disaster. So just to wrap this up, we can show here that, first of all, challenges stabilize control, as opposed to kinematics being destabilized. That on the Moon, skipping reduces challenges, and possibly this is what Gene Cernan meant with sense of security, question mark. And this adaptation indeed requires proprioceptive feedback, although here we cannot directly show, and we are working on this, that it is the main driver of it. And just a couple of ideas for the future and for what we are working on in Nicola's lab. Of course, there must be some spinal premotor circuits, CPG-like central pattern generators, like perhaps, that may drive this gravity-dependent adaptation, gated by, here I'm not writing proprioceptive because there might be other sources of somatosensory feedback that are at play, such as cutaneous, for example. But to do that, we need to keep on going back and forth between human, mouse, and keep on doing this kind of translational studies. So thank you to all the people, because when I say we measured 12 people, I didn't do that. This was all Gaspare, Valentina, Francesco's work. But thanks to all of you, and thank to the two of you for the invitation.
Thank you very much. I can also say, although I'm not an astronaut, that I felt more stable while doing skipping on the Moon. So yeah, we have it. We got it. Question about skipping on the Moon. I will start with a very important professor, and then I will jump back.
Kill yourself.
Thank you. Thank you very much. Fantastic presentation. Thank you. You're absolutely right that the proprioceptive input is fundamental for locomotion, because it sets the timing of locomotion. The proprioceptive contact with the foot and the skin receptors regulate, activate the rhythm center that generates the pattern of movement. So
yeah, definitely.
You remove that, yes.
Definitely, and of course this is not new. We knew this from the cats experiment of the 70s and 80s. However, you mentioned also skin receptors. I and Nicola completely agree with you. There's more to it, and sometimes different sensory feedback mechanisms contribute to proprioception, although they are not the classical spindles and GTOs.
And I also, sorry, I was wondering that because locomotion involves a stretch shortening cycle, obviously a slower transition from one step to the other, it really alters the stretch shortening cycle and the behavior of the muscle and tendon.
Yes, so usually what we see is that there is a much shortened, a much lengthened stance phase and a much shortened swing phase. Yeah, exactly.
Thank you.
It's a very simple question. When you say that challenges stabilize control, does this mean that falling down is less probable when there is a challenge going on, or what do you mean with that?
So,
The challenges stabilize the system.
So I want to make clear that when I say system here, I mean that I'm talking in the space of muscle activation patterns. So the actual whole system, big picture, kinematics or so on, we don't see it. We just see what happens at a central level, right, in the control of it. And what we see is that activation patterns become more stable, and our explanation is because perturbations or challenges put some constraints on the system. So you're not allowed to roam free with your activation patterns anymore.
You have to talk, so you come down just for talking. Right now, you come down. One more question? Quick one? Yep.
Thank you very much. It's always funny. Do you think that if humans spent, let's say, months on the moon, their gait might change? Or this is only a result of an acute exposure to microgravity?
I would say definitely. And one of the reasons I can answer like that, it's because mechanistically we can show that if we take proprioception from mice, and we follow them up in a longitudinal study, they keep on degenerating because they lost proprioception, and if we train them, we can at least sustain this delay, these problems that they have. So certainly, on the moon, proprioceptive input changes, so locomotion is going to be different on a long term.
Thank you very much. If you have more questions, there is the coffee break in some time.